Okay, so the next reaction is another enolate reaction, only now we're going to react, instead of reacting with a ketone or an aldehyde, we're going to react with a ester or an acid chloride. And so now we're talking about things that were on the waterfall diagram. And remember, on the waterfall diagram, all of our reactions ended up being carbonyl substitutions, right? We replaced the chlorine with something else. We replaced the oxygen group of the ester with something else. And that's exactly what we're going to do here. So if we know kind of what acid chlorides do and what esters do and what types of carbonyl reactions they do, and we know what enolates look like, we can pretty much just predict what's going to happen here, even without having to really learn a whole new process. Right. This reaction is called the Claisen condensation. Claisen condensation. Or just the Claisen reaction for short. And the Claisen condensation is going to be an enolate plus an ester or an acid chloride. Usually we use esters, but acid chlorides also work. And what you're going to get out is you're going to get a 1,3 dicarbonyl. Okay, so first we have our enolate. So let's use, we'll just use an aldehyde enolate. We can take this, we can treat it with a base. I'm going to use sodium methoxide. And that's going to, as always, remove a hydrogen from that alpha position neighboring the carbonyl. We're going to make the pi bond, we're going to break the carbon-oxygen pi bond, push electrons to the oxygen. Right? So making the enolate looks the same as it has in all our previous examples. And then when we have, once we have that, we bring in our ester. And I'm going to use, I don't know, we'll use a 5-membered ring. And so our ester group is going to react as every ester group we've seen so far reacts, right? We're going to reform the carbonyl. We're going to push these electrons over here. So the alpha position is going to be the nucleophile as always. The nucleophile adds to the carbonyl. We break the carbon-oxygen pi bond. We push the electrons up to the oxygen and we get a new carbon-carbon bond between the alpha carbon here and the carbonyl carbon here. And so that's going to give us an intermediate that should look familiar. Right? Whenever we add a nucleophile to an ester, we get things that look like this, where we have our leaving group, our OCH3 here, we have our O- here, and then we have, this is going to, so here's our carbonyl carbon, this is going to be our alpha carbon, and so we're going to have our carbonyl over here, aldehyde, and then we have 2 additional carbons attached here, so yeah, something that looks like that. Right, so once again, we have kind of 2 parts of this. We have, this was our enolate, the circled part is our enolate, the other 6 carbons over here are the ester. And then naturally, of course, we're going to reform the carbonyl and kick out the leaving group. We're going to make a ketone in this case and kick out the leaving group, and we'll end up with this kind of thing. And once again, if we want to kind of break this up, right, we have 2 parts of this. We have the 6 carbons over here that came from the ester, and then we have the 4 carbons on the other side that came from our enolate. And notice that we're connecting the alpha carbon of our enolate, right? Because that's where enolates are nucleophilic. We're connecting the alpha carbon to the carbonyl carbon of the ester, right? And so if we do that, because the alpha carbon is always next to the carbonyl, we're always going to end up with a carbonyl on carbon 1, a carbonyl on carbon 3. So 1, 2, 3, just like that. The products will always look like this with carbonyls. You'll have 2 carbonyls with a carbon spaced in between them. Right? The Claisen condensation always works like this. It's a substitution reaction where the enolate adds to the carbonyl, then you kick out your leaving group, and you get um, this 1,3 dicarbonyl for a product.